We're in section 13.4. Before we go on to example 2, just recall that we can use integration as a tool to move backwards when we know a derivative and we want to go back to the original function. And so specifically with, say, velocity, if we wanted to find the position function and velocity was known, we could use integration to get back to position. And that's because velocity is a derivative of position. Fundamental Theorem of Calculus Part 1, back from Calc 1, essentially allows us to do that. The integrating and taking the derivative are undoing each other. There's some details in there, but that's the essence of the idea there. So let's go ahead and do example 2. We're given the acceleration vector as 2I plus 6tj plus 12t squared k. And that describes the acceleration of a particle. Also note the initial velocity is 1 unit in the x direction, and the initial position is 1 unit in the y direction minus 1 unit in the z. And we're charged to find the velocity and position at t equals 1. So, first of all, we can move backwards. Let's start just with one step here. So the acceleration is equal to the velocity's derivative. So we can get to velocity if we integrate the acceleration function, vector function. So that's what I'm showing here, and just showing the different components we have for acceleration in here, and then we just go ahead and do that. So we get 2t, 3t squared, 4t cubed, and then don't forget your plus c, where c is a vector. Alright, so we have this in Calc 1 where we'd have plus c, a constant that's a scalar, but now we have a plus c that is a vector. So to determine this, it's actually given, but to kind of show the details on why and not just telling you, what we can use is the initial velocity. So initial velocity is when t equals 0. And if you plug that into what we have for our velocity function, notice first of all, I guess, that when it's 1 unit in the x direction, that is the vector 1, 0, 0. So our velocity vector at t equals 0 is equal to that, and then we just set it equal to what we have so far with t equals 0 plugged in. We get zeros here everywhere for this part, and so then it just matches up perfectly with each of the components of c. And so note that that just becomes exactly the initial velocity. So at this point, if you wanted to just skip to that step, that's alright, but in this example I'm showing those details instead of just stating it and not explaining where it comes from. So there we go, we can move on. We're trying to find the velocity at t equals 1, but we also need to find position. So let's keep going. Actually, I suppose we should write this together. Sort of forgot about that. So with the constant c written together, notice it's 1, 0, 0. If we write that together in terms of ijk with the components, then what we'll have is 2t plus 1. So the plus 1 here came from the 1, 0, 0 constant c, and then the rest of them had c2, c3 respectively that were 0, so those ended up being the same. Alright, so I forgot that I did just plug in here. So we'll finish this off, the velocity at time equals 1. Now that we got our full velocity vector taken care of, we can just go ahead and plug in that t equals 1 and get our result. So we get 3i plus 3j plus 4k. I was excited to do more integration. Now we can move on and actually do that. Here we have our velocity vector, and to get to position, we're going to integrate. So we can do this term by term, or component by component, and term by term, and we'll get the following. we get 2t plus 1 integrating into t squared plus t, 3t squared to t cubed, 4t cubed to t to the fourth, and then plus another constant, which I'm just calling k, because it could be different than the c. And here we play the same game with a given. We're given that the initial position was equal to, scroll back, 1 unit in the y direction minus 1 unit in the z. And so putting those two pieces together, our big K, the constant, is equal to 0, 1, negative 1 in vector form. So setting this up, our position, our initial position, our position at time equals 0 is equal to 0, 1, negative 1, and then plug t equals 0 into the answer we found for the integral, and we happen to get all zeros again, and so then we can match up perfectly the components in K with our initial position. So putting that together again, for the 0 here initially in the x, we don't have anything to add for the x component, but for the y and the z, we do have some things to add on there, a plus 1 and a minus 1. So last thing was we were charged to find the position when time equals 1, so plug in 1 for t, and we get our final answer for our final thing we were asked to find. So our position at t equals 1 is 2, 2, 0. So I'm going to stop the recording here and then pick up with another one for the next part.